Hello students, let's learn flow through an annulus. In chemical engineering, we often come across flow through an annulus. A typical example is heat exchanger, shell and tube heat exchanger, where we want to know the fluid flow behavior through annulus. So what is annulus? Annulus is, let's consider two concentric pipes like this. There is a pipe inside a pipe, so when it creates this annular space, and this is called an annular flow. Here is the annular space. So this is flow through an annulus. Annulus flow is a term used in oil and gas industry to describe flow of fluids in space-time to concentric pipes, such as space between the whale casing, production tubing, which is typically sought in highly productive wells, through where a tubing flow can limit maximum production rates. So we get maximum production rates like this using tubing flow. With annular flow, the gas is injected down the tubing string and fluids are produced from the tubing annulus. The production of optical fibers, where glass preform is melted and drawn through an annular orifice to create the fiber. The design of certain types of filters, where fluids are passing through annular space to remove impurities. We can see this in water treatment plant or for the treatment of water. To understand fluid flow in annular space, consider two pipes having same center of radius kr and r, where outer pipe have radius r and inner pipe have radius kr. Which is therefore K is the ratio of outer pipe upon inner pipe, inner pipe upon outer pipe. Now this cylindrical pipe have radius length L, at which fluid is flowing in annular space, that is space between these two pipes. If you see it like this, now here at z equals to 0 and at z equals to L, this flow is opposite to the gravity, and flow is due to pressure. Pressure is P naught plus rho G naught at z equals to 0 and PL plus rho GL. Now consider a shell to find the momentum flux. So this kind of shell is I am considering here. This is the shell. If you see, the shell is look like this if you see it in the front. This is the inner pipe of radius kr and outer pipe of radius r, and fluid is flowing in annular space. Now this is kr. Considering shell at distance small r, delta r, r plus delta r at this shell surface. Yeah. This outer cylindrical pipe have radius capital R. Flow is in z direction only, opposite to gravity due to pressure. Therefore velocity Vz. In r direction and theta direction there is no flow. Therefore velocity Vz and V theta is Vr and V theta is equals to 0. Now to find momentum flux, it's due to shear stress acting on it. So to find momentum flux on the shell, shear stress acting on it is tau rz at r and z direction, which is like this, and leaving the shell is tau rz at r plus delta r. So force is acting on fluid. So force per unit length is equals to P naught plus rho g naught minus P naught plus rho gl, PL plus rho gl. So this is equals to upon per unit length. So this is equals to P naught minus PL upon L, where momentum flux in z direction, because fluid is flowing in z direction, is equals to tau rz at r minus tau rz at r plus delta r into 2 pi rl, cylindrical pipe acting on cylindrical pipe. So only conductive momentum is considered, and convective momentum is equals to 0, because whatever fluid is entering is coming out. So convective momentum is considered 0. They are balancing each other. Let us consider fluid is flowing in annular space between two coaxial cylinders of radius r and kr, where k is the ratio of inner cylinder, radius of inner cylinder to the outer cylinder. There is a flow which is upward in direction. It's opposite to gravity. Now this cylinder is of length L, steady state condition, laminar flow, incompressible fluid, density rho and viscosity mu is constant. Flow is only in z direction, therefore velocity Vz, and velocity of at r direction at theta direction is 0. Newtonian fluid. Considering a shell at distance r of thickness delta r, no end effect to find momentum flux, no end effect, whatever fluid is entering is coming out at the edges. There is considered no disturbance of the flow of liquid at edges. Flow of fluid is under pressure. P naught is pressure at z equals to 0, and PL is the pressure at z equals to L. So applying momentum balance at the shell, we obtain rate of molecular momentum in across surface at r 2 by rl at r minus rate of molecular momentum out across surface at r plus delta r, that is 2 by rl tau rz at r plus delta r plus external force acting on fluid, that is 2 pi rl into delta r into P naught minus Pl upon L equals to 0. Now dividing by 2 pi delta r L and taking limit delta r tends to 0, what I got, tau rz r minus tau rz at r plus delta r into r upon delta r taking limit delta r tends to 0 plus P naught minus Pl upon L into r equals to 0. So what I got here, d by dr r tau rz equals to P naught minus Pl upon L into r. So on integration, I got r into tau rz equals to P naught minus Pl upon L r square upon 2 plus C1. So to find the value of C1, we need to put it into boundary condition. So if you see the diagram, at r equals to lambda r, at smaller equals to lambda r, tau rz is equals to 0 and velocity is maximum, while at kr, at distance kr and r, velocity distribution, velocity Vz is equals to 0 and tau rz is maximum. So to put value of tau rz equals to 0 to find C1, what we get here, what we have to put, r equals to lambda r. So putting r equals to lambda r, I got C1 equals to minus P naught minus Pl upon L plus into lambda square r square. So substituting this value in instead of, in place of C1, what I got. So for no shear condition, solid liquid interface, I need tau Rz equals to 0 at x equals to lambda r. I got C1 equals to P naught minus PL upon 2L into lambda square into r square. So substituting this on equation for tau Rz equals to P naught minus PL upon 2L, taking r common, I got small r minus capital R into lambda square r upon small r, where tau r is equals to minus mu dvz upon dz by Newton's law of viscosity. So putting this P naught minus PL upon 2 mu L, taking this mu here, I got this equation. Now integrating this equation by variable separable method,
velocity will be maximum, the shear stress.
this equation becomes Vz equals to minus P naught into PL upon 2 mu L into capital R minus lambda square r into r dr. So this equation becomes Vz equals to P naught minus PL upon 2 mu L r square upon 2. So this becomes 4 mu L into r square into r square upon capital R square minus 2 lambda square ln of r upon small r plus C2. So to find value of C2, there are two boundary conditions at small r equals to capital R and at small r equals to kr, that is here at kr and at capital R. So to find this,
Molar equal
this velocity distribution at both condition is 0. Here you see. So Vz equals to 0 for both conditions. Now putting these values, I got C2 equals to minus 1 and C2 equals to k square minus 2 lambda square ln of K. This with minus sign. So putting this value on equation 3, I got Vz equals to P naught minus PL upon 4 mu L into R square into 1 minus R upon capital R whole square minus 1 minus K square upon ln of 1 upon K into ln of capital R upon small r. So this is the velocity profile, equation for velocity profile. Well, here I had equation for tau rz. So to find maximum velocity, we need to put small r is equals to lambda r. Then we get Vmax at z equals to P naught minus PL upon 4 mu L into r square into 1 minus lambda square 1 minus ln of lambda square. Now what is the average velocity? So average velocity is equals to volumetric flow rate to the area. So 0 to 2 pi 0 to r Vz into r dr d theta upon r dr d theta is equals to P naught minus PL r square upon 8 mu L 1 minus k to the power 4 upon 1 minus k square minus 1 minus k square upon ln of 1 upon k. Now this is the average velocity. To find mass flow rate, m, which is average velocity into area into density, gives the equation pi into P naught minus PL into r to the power 4 into rho upon 8 mu L 1 minus k to the power 4 minus 1 minus k square upon ln 1 upon k. While force exerted on solid surface, force exerted on a wall is pi r square into 1 minus k square into P naught minus PL. It gives me Reynolds number. This force exerted is the sum of force exerted on inner cylinder wall and outer cylinder where laminar flow condition is considered. So to find Reynolds number for laminar flow, here is the equation: twice r 1 minus k rho mu average at z into mu. Thank you.